Swayam Prabha. Digital India. Educated India.
So here there are 4 two-time velocity correlations I talked about. Okay, let's just get some idea about how they're going to look like. Z is one time at a later time. Okay, so Z is just nothing but time difference, because we are doing 2 times how the velocities are correlated. I'm going to plot all 4 of them, how qualitatively they will look like. First, let's start with this guy. Again, I want to say this is nothing but at the fixed point. It's an Eulerian 2-time correlation. So you put a velocity probe. For simplicity, let's just talk about x velocity. So in other words, I and j are 1 and 1. We're going to talk about x velocity now, x velocity a little time later. Okay, so just erase this and I put 1 and 1. So that's easy to measure. So you have a hot wire probe or something, it measures velocity. You take measurement now, few seconds later, and the time gap z you keep varying. Okay, and you make many measurements and do average, and you get this. And you get this starts at 1 and it goes like this. Okay. Now let's move to this one, and let me change the color. So we now are talking about same x velocity now and a little time later, but not at the same point, wherever the fluid has moved. So I'm just following the fluid. Now I ask you a question. It's going to look like this. It's going to have an exponential decay. Only question I'm going to ask is it going to be shorter or longer time scale? That's a very simple question. So in other words, is it going to follow fast? So because I'm just trying to make us think a little bit. What's the difference between a fluid measuring at a fixed probe versus following the parcel? Remember, if I follow the parcel, will I keep the memory for long or will I be short? What do you think? For a longer time, because I am writing the eddy. So when I fix the probe, the eddy may be swept out. So if I have an eddy, that eddy is being swept by a larger eddy. So that fixed probe will see any eddy only for a short time because it's being swept away. Whereas when I follow, I'm riding with the eddy. Therefore, excellent, some people answered. So this is how RTUC. Don't worry about this notation I said. You understand that this is how. So in other words, going from fixed probe to following the fluid parcel, I have more memory. Okay. Now let's do the other thing. What about this? Let's change the color again of the pen. What about this? Now what I'm saying is that, well, I'm not following the fluid, but I'm going to follow the particle. Okay. Here I need to tell you that it will decrease the correlation, and this is the effect called, very famous effect called crossing trajectory effect, because the particle is falling down. It cuts across eddies, so it moves, bulldozes past the eddy. Therefore, I'm just being very qualitative here. Okay, I'm not giving any numbers. So going from tracking the fluid versus tracking the particle, I have what is called crossing trajectory effect. So I'm going to cut across eddies. So how far will I get? Close to red or shorter than red? I don't know. It depends on the problem. But all I know is that the new one that I'm going to draw is going to be less than yellow. How much, I don't know. Okay. So that's an interesting effect that, hey, a Lagrangian particle. So now when the Stokes number of a particle is close to, if it's very small, the orange one and the yellow one will be similar because he's just tracking the fluid. Incredibly, and by the way, it can also be very large. So in other words, it depends on this is small Stokes number. It just quite not following the fluid, is cutting across eddies. On the other hand, if you think of a baseball, it may remember its velocity for a long time because it doesn't care about the fluid at all. So its velocity. So in other words, how the orange line will behave depends on Stokes number. For small Stokes number, I may go down. For large Stokes number, I may even remember for a long time. Okay, so that's something for you to keep in mind. The last one is, I'm not talking about the fluid velocity, but I am talking about the particle velocity following the particle. But due to the inertia, this may go up. So if I use a green color for this, no, it's not green. Like this, okay. So the point I'm trying to make is, we are interested in the area under this green curve, which is t time scale following the particle, 2 time velocity correlations time scale. And we are interested in how it is related to Tt, which is Eulerian 2 time correlations time scale, okay, which is the red color one's time scale. Now, I will give you an expression, an equation, this in terms of this, but I wanted to understand why they are different physically is because of these different mechanisms that I talked about. Okay, so going from tracking the particle to fixed probe, there's a lot of physics in there. So we want to build these things. These are developed by some people like Lianping Wang and so on and so forth. Yeah.
Question on the baseball comment. So then for that, when we're looking at the third correlation, that is particle follow the particle but track fluid velocity, so that will be really low, right?
Here we are talking about how velocity of something is correlated to velocity of that particle or fluid, whatever it is, at a later time. If you follow a very, by definition, inertia means, when you say something has high inertia, it doesn't want to change. It changes on a slow time scale. Okay. Therefore, high Stokes number particles, because of their inertia, are very, very sluggish. Okay. And that's why the decay of the green line is very, very slow, because particles typically have more inertia than the fluid, and therefore it doesn't change its velocity nearly as much.
I'm asking about the
orange line. Okay. Orange line, generally what I'm thinking is that maybe I confused a little bit. If I didn't draw this line, you would have been probably happy. Okay. Let me redraw this. This may be a sufficient picture. From red to yellow, we are going from a fixed probe to following the fluid. So there you're tracking the eddy, so it's shifted to the right. From yellow to orange, we fall down because of the crossing trajectory effect. The particles are bulldozing through. But remember, the orange line is following the particle. You're looking at what is the fluid velocity, and therefore we go down because of the crossing trajectory. We are just cutting through different eddies, so we are losing the information. On the other hand, going from orange to the green, we say we follow the particle, but we want the particle's velocity, which usually shift to the right because particles have, remember. Now, the orange to green may not be a whole lot different if the Stokes number is small, because particle velocity and fluid velocity. But if it's high Stokes number particle, it may remember its velocity for a long time. Okay, did that answer your question?
I'm sort of thinking, sir, with respect to the orange line, for like something with a high Stokes number, the fluid velocity will change very quickly, right? Because it's not concerned about the fluid.
And that's why it moved from yellow, the orange line shifted to smaller time scale.
We expect like even it to shift further, like the correlation should decrease if we are talking about the inertial particle.
Inertial particle, my thinking is, my understanding is that inertia will, here we are talking about, see, remember, three lines are fluid velocity correlations. This is the first time we are talking about how particles velocity is correlated, and I'm saying particle velocity, high Stokes number, particle, when it's moving, it may see different fluid, but it's inertia, so he will maintain its velocity. Think of like a baseball, and you are throwing it in a windy day. As it travels, it sees different fluid velocities. It's cutting across different eddies, and therefore fluid velocity tracking the particle will die. It will fall off very fast. But we are asking the question in the green line, what is the particle's velocity now and a little time later? You say, yeah, you threw it at 80 kilometers per hour, it's going to be quite close. Okay, it remembers for a long time. On the other hand, if you take a micron-sized particle in turbulence, it just follows the fluid, so it doesn't have a whole lot of inertia, and therefore the orange line and the green line may not shift that much. It's just a qualitative statement in the sense that the main thing that I wanted to talk about is, if you're tracking fluid parcel, you're following it, you will have more memory. But if you are going to follow the particle, you will lose something because of the crossing trajectory, but you will gain something in terms of the inertial effects. So a lot of complex process. And there's you can read the papers by Wang and Stock, and there are lots of really good references. I mean, they are given in my in the book. Okay, I have never worked on this, but they have done a good job. Okay, so what I wanted to do was talk a few more things about. So sort of in way of summarizing, what I will say is, we really want to know two important quantities about the particles, which is, in turbulent, what's the fluctuating velocity of the particles? Now remember, it's not going to be fluid velocity fluctuation. If particles are really small, then they may be the same. Fluid velocity fluctuation is the same as the particle velocity fluctuation. On the other hand, if particles have large inertia, it may not want to change this velocity. So imagine, think of like a particle falling down in a turbulent flow. A very turbulent flow is being buffeted left and right and so on. A tiny particle will just go follow the fluid, and its fluctuating velocity will be large. Change the particle size or make it very dense, it probably will cut across and will start falling down. Maybe it might go a little bit this way and that way, but it will just pretty much follow its course. So V prime square, which is fluctuating particle velocity, when it's very small, could be U prime square, the fluid velocity fluctuation. And it's very inertia, it's remembered for a long time, and the fluctuation may not be that big. Even if turbulence is very heavy, particles may not be responding to all that turbulence. Same thing with the integral scale. What about how long a particle remembers its fluctuating velocity? So here the first one is how big is the fluctuating particle velocity. Here this quantity is how long does it remember, because those are the two things that we want in Langevin model. Okay. So here this time scale on which particle remembers its velocity, that's what I explained in the previous slide, how it changes with varying effects. Okay. Ultimately, I said that maybe we might need particle diffusion coefficient. So these are the sort of three quantities related to particle we are interested in, and it depends on particle size or the Stokes number, density ratio, and things like that. But what do we have in a RANS or LES? This is what we have. So what I'm saying is that in the previous slide I said what we want to describe particles, but this is the slide on what we have. Well, when you simulate in a RANS, you will get fluid velocity fluctuation. This comes as kinetic energy K. Okay, K, you know what it is. Now this you typically don't have. This is the length Eulerian. This is fixed probe, since they say Eulerian. So you measure a fixed probe, and you two-time correlation. What's the time scale of it? That's this. This is the information you may not typically have in your RANS simulation, but from K and epsilon you can make a very good guess of what's the time scale of turbulence, what's the length scale of that turbulence. So these things, you may not directly get it, but a RANS or a LES simulation, you will know it. So bottom line is that these are the things in a RANS simulation or in a LES you will have. Question is, how do you get these? Okay, so that's what I wanted to spend a minute, unfortunately. Okay. So I wanted to show some results, but before that, maybe I will just go straight to the result. Okay, I'll skip some details here. Okay, so here it is. Okay, people have done this calculation, and they think that, so what is being plotted here is here, this is for a sedimenting system. So what is being plotted here is particles' vertical velocity, say z, fluctuating vertical velocity square divided by fluid fluctuation velocity square. So in other words, this in the vertical direction, this is in the horizontal direction. Let me put for the fluid, since it's isotropic turbulent, the denominator is the same, is x and y velocities are the same. So here we are asking a simple question: if I know how much is the fluid velocity fluctuation in an isotropic turbulence and particles are falling down, what would be the vertical velocity fluctuation if you have millions of particles falling down? What the vertical velocity fluctuation is? Is it as big as the fluid velocity fluctuation? And what is the horizontal velocity fluctuation? So now there is a difference. Even though the fluid is isotropic, since the particles are falling down, the vertical direction is different from the horizontal direction. And it's quite clear that from these plots, and then what controls this is the Stokes number of the particle and the mean settling velocity of the particles, and this is nothing but URMS. So here this is URMS, that's the same thing, which is also square root of k, okay, in isotropic turbulence. Okay. So the question is, depending upon how fast the particle is settling down and what is its Stokes number, which depends also on density ratio, you could have fluid velocity, vertical velocity fluctuation and the horizontal velocity fluctuation are typically much smaller. This is what I was talking about earlier, that particle velocity fluctuation will always be a little dumber than the fluid velocity fluctuation. Okay, but here everything is done for a solid particle. If you go to a bubble, things may be different. A bubble can fluctuate more than the fluid.
Buoyant particles. This is buoyant particle you're talking about, or the
What do you mean?
particle velocity? You have mentioned that it's lower than the fluid velocity.
Yeah. It's the fluctuating component. That's why I put a prime here. So the mean velocity has been subtracted. So in other words, when you look at particles, they're all falling down, but they're all having also deviation from the falling velocity. So we're asking how much is the particle velocity is fluctuating.
Density of the medium and density dispersed phase both are same or different? Density of the dispersed phase and the density of the continuous phase both are same or different?
What of the dispersed?
Is it like a buoyant particle you mean to say that?
It's heavier particle. These are particles that are heavier and they are falling down. My hearing is pretty bad, and you're having a very soft voice. So the bottom line is that a particle velocity fluctuation will decrease, except for lighter than fluid case. It could be larger. So there are similar plots for bubbles, but this is for heavier than fluid particles. Depending on the Stokes number and the relative settling velocity, this gives you how particle velocity fluctuation is changing. And this is the paper I was talking about. So it's done by Lianping Wang and Dave Stock, a pretty old paper. And this one is the time scale. So the same thing as before, I said that this will be again the horizontal direction. Okay. So this is in the x direction, and in the z direction. So how long a particle remembers its horizontal velocity fluctuation is in this plot, and how long does a particle remembers its vertical velocity fluctuation is in here, compared to how a fluid remembers its velocity at a fixed probe. So in other words, everything is non-dimensionalized. So we take, so with this non-dimensional quantity, it does decrease. In other words, a particle could forget faster at low Stokes number. But when Stokes number increases, you see, particle remembers its velocity 20 times longer than a fluid would do. So you can see that the x direction, the horizontal direction, there is little difference between horizontal direction and the vertical direction because of the preferential fall of the particles. But the lesson, the general lesson is that small Stokes number particles forget because of the varying effect that I was talking about, like crossing trajectory and so on and so forth. But when Stokes number increases, the inertia effect of the particles becomes important, and the time scale of particle velocity is much larger. Okay. So that's my last slide on this topic, and I want to go to a slightly different topic. Any questions on this? So there's a lot of details. So the next thing I want to talk about is what happens when a particle gets close to your wall. Okay, particle wall interaction becomes important. Okay, so so what I wanted to talk about was when a particle is close to a wall, I want you to think of 3 different length scales. First thing is the size of the particle. So diameter dp. And another one is L is the distance. sometimes I will also call delta. Delta is the separation. They are related. L and delta are off by one particle radius. Okay, so I will sometimes use L, sometimes use delta, but it tells you how far the particle is away from the wall. As a general rule, when L is maybe 5 to 10 times particle diameter, you don't have to worry that you can treat the wall is far away. So that's a general rule from my experience. But when the particle gets closer to the wall, the kind of questions that we are asking is what happens to lift and drag forces. Okay. And the third length scale that I wanted to talk about is what kind of a boundary layer the flow is in. Because typically when you have a particle close to your wall, you are going to have a velocity profile that may look one of these three cases. Where boundary layer is characterized by delta, well, boundary layer thickness, let's call this delta BL just to differentiate it from this delta. Here delta BL is small, okay. Here its delta BL is about the same as L, of the same order. Here delta BL is much larger than L. So in other words, you can think of it this way: the particle is buried deep within the boundary layer in this case. Here the boundary layer is so thin that the particle is almost in a uniform flow. It's somewhere in between. Okay. Most of what I am going to talk about is probably this limit, particle in a shear flow. Okay. This is typically is the most studied area. People haven't studied this cases nearly as much. Okay. Because typically 100 micron, few hundred micron particles, and the boundary layer is few millimeters thick. So you are more like this scenario. Okay. So a lot of what I'm going to talk about is this. So from here on, I'm going to only deal with diameter of the particle and L or delta, how far the particle is away from the wall. Okay. Now I want to point out that there are some really why people got interested. I don't know whether you are familiar with the work of Segre and Silberberg, at least some of you may be. So there are very amazing phenomenon people have observed, that when you have a pipe flow and when you put particles, these guys observed that all the particles concentrated in two layers, not at the center pipe center line, nor really at the pipe wall. Under the right conditions, all the particles accumulated in some layer. That's mainly because this lift force, there is something called a wall induced lift force, which pushes the particle. So when it gets close to the wall, it gets pushed inwards. When it's close to the center line, it gets pushed outward. So they accumulate. So there are lots of very interesting phenomenon, and these are all because of particle wall interaction. Okay, so in multi-phase flow, especially people who are dealing with microfluidics, this becomes a very important effect. Yes.
Sir, this directly connects with yesterday's point of shear induced lift.
Yeah. It is shear induced. In fact, that's the next thing I'm going to talk about, which is so I will get to this in a minute. It doesn't have to be shear induced lift. There is beyond shear. So in this picture, I have drawn the particle with the shear. So your question is very relevant because I want to go to the next thing. In the Stokes limit, you can think of sort of when a particle interacts with a wall, you can think of 5 different problems. I want you to think of 5 different interactions. One is there is a wall and the particle is moving, no shear. This is a very important thing. Think of it this way: you have a vertical wall, you drop a particle or a droplet. Will it go get stuck in the wall or will it move away? Same thing, a bubble rising next to your wall. First of all, one other question I will ask: close to your wall, particle is falling, will its drag be larger or smaller? I think it will be larger because it's more viscous, it's close to it. So how much? 5%, 10%? Okay. The other thing is that will it get, what will be the lift force? Now remember, there is no shear flow here. It's just falling. It's just quiescent fluid, just the particle is falling down. Okay. So because of the wall, if you look in terms of the forces, there will be a drag force, but there will be a lift force. I don't know whether it's up or down. Typically it's up, okay, but under certain conditions it could be down also. And that's why Silberberg's, the previous study that I showed, it moved away from the wall. But here there is no ambient flow, but in that experiment there was a parabolic velocity profile. It was a pipe flow, so the center of the pipe was in good place either. That will push the particle down. Okay. So here I am just asking about what is the effect on the wall. So this is, let me call this translation problem. This is problem number 1. Second problem is a fixed particle in a shear flow, and this is why this is what I said earlier. I'm not going to consider a thin boundary layer, etc. I'm going to assume boundary layer is much thicker than the particle. Therefore, particle is in a linear profile. It's deep within the boundary layer. Okay, so you can change that if you want to make the problem more complicated. So all of them I'm talking about in the 0 Reynolds number limit, and I'm talking about steady flow. Okay, just to start making you think that, you know, particle wall interaction could happen. Many different physics are buried in this, depending upon how the particle is moving and how the flow is moving. The third case is the particle and it's rotating. So in other words, if you put these together, you get a particle moving in a unrotating, spinning close to a wall. Okay, so these are the 3 problems. Now this is not enough.
All the cases are these particles are near the wall.
Yes. In other words, L, the distance, is of the order of or proportional to or roughly equal to diameter. So it may be, the distance could be maybe 3 diameters from, that's why I first said that if that distance is 20 diameters, forget all these things, forget the wall. So everything I'm talking about is a particle close to a wall, and the Reynolds number is small. Okay. So what's the fourth problem is particle could be moving towards the wall or away from the wall. And what is the fifth problem? Is particle could be spinning about a vertical axis. This describes everything. You put them together, particle could be moving parallel to the wall, perpendicular to the wall, spinning parallel to the wall, perpendicular to the wall, and there is a shear flow. So in the linear limit, any particle close to a wall is nothing but the sum of these 5 problems. In the Stokes limit, now I should tell you, I should ask you this. I said this, I put a question mark. Let me go back here. What do you think is the lift force in this problem? In the Stokes limit, what is the lift force? 0, right? We talked about that. So in Stokes limit, there is absolutely no lift. So there is no lift in this problem. Okay. Every force is drag force, but there are 5 of them, and you put them together, and these 5 problems have been studied. Lots of work, and I don't have time, and it's not necessary.
So this is applicable only when Reynolds number of the system is close to 0.
Yeah. So this is micron size particles moving in close to a pipe flow, droplets going in a tube. There's many applications. Okay, so any microfluidics will be very relevant. Yeah.
For example, industrial scale, if you consider for a spray dryer.
Oh, then this will not work, and I will talk about that later. So let's start walking before we run. Okay, so let's try. See, always the strategy that I find it very convenient is that in these limits, there's so much understanding people have. Let's first learn what they have done, because once you go to finite Reynolds number, there is no theory. You have only correlations. So if you don't want correlation science, but you want some science in it, you start with something that easy people have done, and especially in this 5 problem people have done, they have written everything, all the drag law, lift law, everything. So if fortunate, if one is working on a microfluidics and want to track a particle in a pipe flow, there's fantastic results. Okay, and you can use and you can get, but finite Reynolds number is hard. Yeah, I will talk about that. So all 5 problems, I'm going to skip the details because everything, all 5 problems answers are in the book. Every one of them, drag and torque on the particle, there are exact expressions. Okay, and only one thing that I want to tell you is that those results typically are done for 2 limits. One, small gap. Small gap means this gap, which I talk delta, when delta by diameter is very small, this this is dP in my notation, they will use what is called lubrication theory, and they exact answer, very nice answer they will find. When this delta over dP is large, by which not very large, but greater than 1, there is a method of reflection, there is a method. So these are all Stokes flow, but Stokes flow with a wall, it's not that easy, but people compute it. And I have all the expressions, and I don't want to spend the time to give all the relations. Let me just go straight to the answer. Okay, okay, that may be easier. So I will skip a few slides, and here is the answer. Okay, this is done by a really wonderful paper, Goldman, Cox. Okay, most of you weren't born then. Okay, so these guys solved that problem, since it's low Reynolds number, they solved it. So this is the translation problem. And this is the shear problem. So this is problem 1. This is the answer for problem 2. And what is plotted here is force on the particle and the torque on the particle. So translation, again, let's remind ourselves what it is. You have a wall, particle is moving, falling parallel to the wall, and that wall, there will be a drag force on the particle, and the particle will also be now spinning. A particle falling away from the wall will not spin, but particle going parallel to the wall will spin. Now, it's interesting that somebody asked yesterday the question, so the particle moving, it's now spinning, now it may have a magnus at finite Reynolds number, not at 0 Reynolds number, but at finite Reynolds number, the spin because of the wall. So the wall may directly want to push it, but also the spinning, by making the particle spin, it may add additional lift on the particle. Okay, so interesting thing. Now look at this. So this is in the log scale. This is particle in a shear flow. Okay, this result is particle in a shear flow. So when you have a particle and a fluid is coming, this is about 1.6. This is non-dimensional. In other words, what plotted is the drag compared to away from the wall, just the Stokes drag. So in other words, wall increases drag by 60%. Okay, wall increases the drag 60%. Now, what about translation? It goes to infinity. Well, that makes a lot of sense. When you are very, very close to the wall, you can move the particle really, okay, because there is what is called a logarithmic singularity, okay, because you have to squeeze that little layer of fluid away. So dragging a particle when it is very close to your wall is very hard. If wall is super smooth, typically walls are rough, so that's not an issue. But you can roll the particle, but you can't drag the particle, okay, because the drag force increases. Now, on the other hand, you can see the same thing, the two cases. Translation means falling down, and shear means, maybe this is a better example. So the particle is fixed and the flow is shear flow. Okay, so the torque for the shear is given here, for the translation is given here. Okay, so these are the results, Coxman. So these are the results for the problem number 1 and 2. So here you.
The case when the particle is settled on the plate, and then there is a shear flow applied in it, or the translation flow applied in it.
Yeah. So if the particle is touching the wall, then delta goes to 0, right? But typically the delta never perfectly goes to 0, okay, because of the surface roughness of the. So it can get as close to the plate as the roughness of the particle or the roughness of the plate is. So the force will be tremendous if you want to drag that particle. If you put a shear flow, the particle will experience a force, but it may not move, because
It will actually also rotate and move.
it can rotate. If it is rotate, then there are similar results. Okay, for a rotating particle on a plate, a rolling particle, that's the right word, there are results.
I am not talking about giving the rotation to the particle. I am talking about the rotation which will create by the fluid.
Yeah, that's what, when you have a particle close to your wall and you apply a shear flow, it can't slide. That's what I'm saying. It will,
Depending upon the type of shear.
any kind of shear, it will have to roll, because the cost of sliding is tremendous. Because sliding means the particle has to displace the fluid, the thin layer of fluid, it has to squeeze out. But rolling is a better way of it moving. So answer to your question is, if you have a small particle close to your wall or sitting on a wall, rough wall, and you apply any kind of shear flow, it will tend to roll and move forward rather than slide and move forward.
It will follow the same. It will go back to the demonstration. So it will just follow the same path.
No, this is not the path. This is this is force.
Force versus delta.
Yeah, force versus. So when a particle is sitting on the wall, delta is really small.
Let's say 10 is to minus 7, 10 is to minus 10.
Oh, probably then the force will be tremendous, as you can see. Yeah, it just logarithmic singularity. That's why it can't slide. It will have to roll. This is for sliding. So problem 1 is particle sliding. Okay. So what happens is that now you have to combine. When a particle is rolling on the wall, you have a little bit of 1, 3. The particle is rolling. Okay, and they combine in such a way that the force can come manageable and it will roll on the wall. the details you have to put it in. But answer is always is there. So you just have to pick your delta based on your roughness, and you have a force, you have a torque, you have to find whether your particle, what the rolling. So everything is there. You have BBO equation of motion. Now all the forces are there for you. You put them, and people have done that, and they can calculate how a particle moves close to your wall when the Reynolds number is low. That's a solved problem. Okay, so I'm just introducing the details. I'm skipping, but you can go and look at it. Okay, so particle motion at very low Reynolds number close to your wall is a done deal. No more research. So this is the same thing if the particle. So this is what I was talking about. A rolling particle. This is a particle if it's rolling. So you said delta is 10 to the power minus 3, 4, something like that. Now you go and you see that there is a force. To roll the particle, you got to apply a lot of force. Okay, and the torque also goes to infinity. So you have to. So now you have a sliding motion and the rolling motion, and they have to cancel perfectly each other. Okay, that's the kind of rolling motion that you will have. And problem 4 and 5 are less interesting. Okay, so but you can see that people have solved it, and they can give you exact how the force changes. There are precise relations. They are all given in the book, so you can look at it. So in conclusion, what happens is that people solve the small gap, very small gap, using lubrication theory, larger gap using method of reflections. And the most interesting thing is, I said 60 and I'm wrong. The flow induced drag increases in a shear flow. The drag, the wall effect is very strong, increases drag. There is lift force, there is no lift force in the zero Reynolds number limit. And there is a logarithmic singularity. In other words, if you want to roll the particle or drag the particle, the force is pretty large. And then the other thing I want to point out is that now you see a plate is there, particle moving, translation, but you don't only have drag anymore. You have torque coming in. So in other words, a moving particle has to spin, and a spinning particle has to move. So in other words, you see a cross coupling because of. So if you have an unbounded flow and you're spinning, it doesn't know which way to move. But the same spinning particle you put close to your wall, it will start moving forward. Okay, so those are the interesting physics of wall interaction. So we will stop there. When I come back, and I will say a few more, little more interesting details about wall effect. One way to think of this is wall is a gigantic particle. So we're just talking about particle-particle interaction, but one particle small and another particle huge. Next, I will go to particle-particle interaction, the real multiphase flow. So in the afternoon, we will talk about, as volume fractions increase, what happens. So this particle wall interaction is a good starting point to see how two particles are going to interact. Okay. Thank you.